Last year in teaching this course, we didn't specifically present this information with a consolidated diagram like this. And so this is one of the things that I determined I learned from last year that might be helpful to you, just to teach using this diagram. And again, this isn't in the Apologia textbook that I've seen in the new edition, but it is a good way, I believe, of helping us understand the significance of this concept of moles. We had a class in here just about the whole concept of mole, what a mole was, and then the next 2 days the section in the book is entitled Using the Mole Concept in Calculation. So one of the key things to understand about using it, I think, is depicted here in what's called the molar bridge diagram. What is one of the most popular language software programs available today? Rosetta Stone. Does anyone want to tell me the significance of not the company Rosetta Stone, but the actual Rosetta Stone? Okay. It's actually an accidental discovery. It was found in the sand, one of those kind of like, oh, I hurt my toe. What's this rock? Oh, the rock has a little design on it. Let me get the rock. Hey, it's not a little rock. It's a tablet. It's a big rock tablet. Hey, wait a minute. There's a whole bunch of writing on this tablet, and I only recognize a little bit of it. And what they determined was the Rosetta Stone was actually a stone that had the same words written in Greek and in Egyptian hieroglyphic, and I believe it was Persian. I believe there was another language on it as well. But the key point I want you to get is the Rosetta Stone helped us come to understand Egyptian hieroglyphic. When you go and you see the pyramid and these Egyptologists go there and say, well, right up here it tells you that the Pharaoh had a son and da-da-da-da-da. They're translating all that hieroglyph. How do they know what it means? They determined all of that from the Rosetta Stone, because the people who had the Rosetta Stone could understand the Greek and they could see the Egyptian hieroglyphic, and they said, well, they're communicating this idea, and it became a way of translating from one language to the other because they were able to decode the Egyptian hieroglyphic. Kind of in the same way, I want you to consider this molar diagram as your Rosetta Stone for chemistry. This diagram right here is going to help you with some of the relationships we've been talking about. When Mr. Baker is up here and says, if you want to determine the number of moles, you need to take this and divide it by that and multiply it by the other and all that. It gets so confusing. And I might encourage you to memorize one formula and then just know how to manipulate it. But hopefully this diagram will help you see the relationships so that you understand them a little bit better. I grew up in a very DOS kind of a world. I'm used to a DOS prompt or a command prompt, and I can enter in the code and get the computer to do what I want. Most of you have never worked with command prompts and DOS. You tend to work with Windows or visual GUIs, graphical user interfaces. Okay, so you're used to seeing things to come to understand it in terms of pictures. So this is a picture to help you understand this whole idea of moles. And I'm going to encourage you to think of moles as the magic interface between all of these different concepts. The concepts of how many atoms or molecules do I have? What's my actual count? And the concept of how much mass of this material do I have? We're going to see later this concept of molarity. How much stuff do I have per any given volume of any given volume? And down here, this volume of ideal gases. What is the actual space taken up by this much of a particular gas at 25 degrees Celsius, at STP, standard temperature pressure? And as I said before, having this diagram is going to be important. Using this diagram in this module, specifically back and forth this way, is going to help us solve a lot of the problems that we have to work out using this concept of mole. What I want you to see from this diagram is that moles relates everything on the outside. If I want to translate atoms, the number of atoms and molecules that I may have, and I want to translate it into how many grams of that thing I have, I can get there by going through moles. And conversely, if I know how much mass of a certain element or compound that I have, if I have a certain mass and I want to determine how many of them I actually have, how many physical atoms or physical molecules I have, I can do that by translating, by moving through moles to get there. Later on, when I know how many atoms or molecules I have and I want to determine the molarity, I can get there, but I've got to go through moles to get there. So we're moving between atoms and molecule counts, grams of matter, the molarity of the matter, and the volume of the matter, all going through moles. The two relationships we've covered in this module are my atom count, the number of atoms or molecules. So this is my actual count. Okay, that's the number. Before it was hashtag, it was number. Before it was hashtag, it was pound sign. Okay, so if you see hashtag atoms or molecules, it's actually the number, the count of, how many do I have of a particular amount of atoms or molecules. And I may be given how many moles I have, or I may be given how many grams I have. But if I'm given how many grams, I've got to go to moles to go to count. I can't go directly, because moles is the Rosetta Stone for translating between these four different ways of describing the matter. All right? So, let's consider this. Let's say that we have a particular number of atoms. I tell you that you have a sample that has this many atoms of a certain element or this many molecules of a certain compound. And I ask you, how many moles of that element or compound do you have? What this diagram shows us is to go from atoms and molecules to moles, or to go from moles to atoms and molecules, I have a conversion factor of what? 6.02 times 10 to the 23rd. What is that number? It's not avocado, okay? It's not avocado's number. It's Avogadro's number. Avogadro's number. And I'm going to write below this AV number sign, aka hashtag, Avogadro's number. Avogadro's number is the key that moves me from moles to my count, or from my count to my moles. So how do we use Avogadro's number? See right here, 6.02 times 10 to the 23rd. Well, look at the arrows. If I'm moving from moles to my number count, what is the operation? Multiplication. So if I have a number of moles and I want to know how many individual pieces I have, I multiply by Avogadro's number. If, however, I'm giving a count and I'm asked how many moles do I have, I divide by Avogadro's number. You see that? How many do I have? I'm given a certain number. How many moles do I have? I divide by Avogadro's number. Given a certain number of moles, how many individual do I have? I multiply by Avogadro's number. And that will move me from wherever I am in moles to my count of atoms or molecules. In the same way, we have a conversion factor if we go from moles to grams or from grams to moles. Can you see on here what that conversion factor is? It says it's either the atomic mass or the molar mass. Okay? Atomic or molar. Now, when it says atomic / molar, what they're getting to is this idea that if you can compute the atomic mass, you know the molar mass, right? Because if you can do the atomic mass and you determine that by looking on the periodic table and finding the atomic mass number of that element, or computing the atomic mass of a compound, a molecule, by adding up the atomic masses of all the different atoms that make up that molecule, if you have its mass in AMU, which is simply adding up all the atomic masses on the periodic table, if you change the units from AMU to grams, you now have the molar mass. You now have the mass of that element or compound that you need in order to have 1 mole. So I often abbreviate that with MM, my molar mass. My molar mass is either 1 mole of an element or 1 mole of a compound. But whatever it is, if I know my molar mass, if I'm given moles and I need to move to grams, what do? I'm going to divide the number of moles divide by the molar mass. If I divide the number of moles by the molar mass, my answer will end up in grams. Conversely, if I'm given a certain mass of either an element or compound, I'm given a mass and I want to move it to say how many moles do I have, I would take that mass and I would multiply it by the molar mass, and my answer would now be in moles. Okay? So by knowing these two conversion factors here, my Avogadro's number and my molar mass, I can move between the different points on this diagram. Now hopefully you would see then, if I'm given the number of molecules or atoms, and I'm asked to compute how many grams of that I have to do a two-step process. I have to convert from count to moles, and then from moles to grams. If I feel comfortable, I could write the math out as one long equation, or I could do it in two parts. I could first of all determine the number of moles, and then as a second set of operations, determine the number of grams. And in the same way, going from grams to moles, and then moles to count. Okay? So everything we're going to need to know in terms of solving problems in this module, I believe, are represented in this diagram. The equations we've had to learn so far, except for the identity relationship of, what is the mass of a single AMU? 1.66 times 10 to the negative 24th grams. Okay, that's something we have got to memorize outside of this diagram. And we hopefully will memorize Avogadro's number. And we should be able to determine the molar mass, looking at the periodic table and finding the atomic masses. So if we know Avogadro's and we know the molar mass, and we have this diagram, we should be able to move around. So given a question that says, given so many grams of this, how many moles do you have? I'm going from grams to moles. I need to multiply by the molar mass. Any questions on that diagram? Is this helpful? Okay, so at least you know process-wise what you're going to need to do to solve most of the problems. As a matter of fact, as we do the on your owns and work some problems here, and as we complete the module, for a while I'm going to try to put this diagram up on the board to help us, okay? But for your exam, please, you should be able to reproduce this diagram. You should be able to use it without reproducing it, but if you need to, be able to reproduce this diagram to help you on your graded events. Specifically for this module, be able to reproduce this lateral section here to help you. Other modules will add this and add this. And so we'll show it again later, because we'll have this one thoroughly understood. We'll say, okay, now let's add the concept of molarity. Or, okay, let's add the concept of volume and see how that relates to the molar bridge. Okay. So a little bit of help from outside the core curriculum. We're going to go ahead and pick up our discussion today on using the mole concept. Third edition, page 265. Second, we're on page 153. Let me go ahead and advance this. We're looking at this equation. We have a CH4 molecule in a gaseous form and two O2 molecules in gaseous form that react to produce a carbon dioxide molecule in gaseous form and two water vapor molecules, two H2Os in gaseous form. Now, ask a question. First of all, is this equation balanced? Because one of the things we're going to have to remember is we're going to talk about some principles and some relationships, but the relationships only work if the equation, first of all, is valid. And we know it's valid either because, A, we produce the right elements from the right, we react the right reactants to produce the correct products, and that the equation itself is balanced. If it's not a balanced equation, it doesn't have any real authority. It's got to be true. Okay, so let's check this one first to see if it's balanced, if this is actually a true or potentially true equation. Because if it's not balanced, we know it's not true. What are the elements that we have on the reactant side? Let's balance it. Carbon, hydrogen, oxygen. Do we have the same on the product side? Any additional? Any lacking? No. Okay, so everything's accounted for, at least in terms of the elements that are used. Yes, sir. 265 on third edition. So carbon, hydrogen, oxygen are good old CHO, right? So many of these things are CHO combinations. Carbon, hydrogen, oxygen. All of our life, carbon-based, oxygenated, it's all over the place, CHO. All right, so we've got carbon, hydrogen, and oxygen. Let's do our counts on the reactant and the product side. For carbon, what's my math look like? One set of 1. Hydrogen, 1 set 4. And oxygen, 2 set 2. So it's 1, 4, 4. So we go down the reactant side. Let's check with product side. Product side, carbon, we have 1 set 1. Any more? No. Hydrogen, 2 set 2. And oxygen, 1 set 2 plus 2 set 1. All right. And 1, 4, 2 and 2 is 4. So we have carbon has 1 and 1, hydrogen has 4 and 4, oxygen has 4 and 4. It's a balanced equation. Whenever you're checking, and some of the stuff we're going to be doing that we're going to be introducing right now, before you can say that it's valid, you've got to check to make sure it's balanced. If the equation's not balanced, what we're about to talk about now doesn't apply. It first of all has to be balanced. All right. So with a balanced equation like this, we've already covered what can we say about this equation in terms of the individual molecules. You've heard me say before that one molecule of CH4, because he implied 1, right? One molecule of CH4 and 2 molecules of O2 react to produce 1 molecule of CO2 and 2 molecules of H2O. You should be very comfortable with that by now. All right. We're going to go ahead and extend this concept now. Because if we can combine 1 and 2 to make 1 and 2, we can also take 1 dozen and 2 dozen. 1 dozen of these because it's a 1, applied 1, and 2 dozen of these because we have a coefficient of 2. And if we've got 1 dozen and 2 dozen, we're going to produce 1 dozen and 2 dozen. Is everybody comfortable with that? I mean, all we've done is taken this and multiplied every coefficient by 12, right? Because that's what a dozen is. So it would be 12 plus 24 produces 12 plus 24, if we're talking about dozens. Any question about that? Everybody feel comfortable with that? Okay, now we need to go just one more step. Rather than dozens, we've said that a mole is nothing more than a unit of counting, right? It's a certain quantity. And so now here's where we take the big jump into using the mole concept. As you say that, okay, if 1 and 2 produce 1 and 2, and if 1 dozen and 2 dozen produce 1 dozen and 2 dozen, then 1 mole and 2 moles produce 1 mole and 2 moles. See? What we've done is rather than taking 1 and 2 and reacting them to produce 1 and 2, we're taking 1 times 6.02 times 10 to the 23rd and reacting it with 2 times 6.02 times 10 to the 23rd, reacting it to produce 1 times 6.02 times 10 to the 23rd and 2 times 6.02 times 10 to the 23rd. All we've done is taken the number and just blown it up huge, right? So rather than having 1 and 1 and 1 and 1 and having this really small reaction, now we have a bazillion and 2 bazillion reacting to produce 1 bazillion and 2 bazillion. But you see, it's proportionally the same. I still, at the very smallest level, I have 1 and 2 individuals reacting to produce 1 and 2 individuals. I'm just doing it 6.02 times 10 to the 23rd times. Okay? Comfortable with that concept at least. That I've got the same thing going on here. For every 1 of whatever count and 2 of whatever count, I produce 1 of whatever count and 2 of whatever count. The same count. They've got to be the same all the way across. And that's the concept in the reactions about using the mole concept. Because 1 molecule and 2 molecules to produce 1 molecule and 2 molecules is too small for me to get any measurable results, for me to to not only not see the reaction, but see, of course, we can't see the reaction as much as we can see the effects of the reaction. But 1 and 2 molecules reacting to produce 1 and 2 molecules, the reaction consequences are so small as to be indiscernible to us. However, if I take those results of reaction and I multiply them 6.02 times 10 to the 23rd times, now I can actually see it. I can see the results of the reaction. I may not see these 2 molecules breaking down and reforming to produce these different molecules over here, but the consequence of it, let's say if there's a phase change, let's say liquids produce gases. Well, one molecule and 1 molecule of liquids, there really is no concept, right? Because it's at the individual level, there's no such thing as liquid, solid, or gas. It's just one atom or one molecule. But when I multiply it 6.02 times 10 to the 23rd times, now I can do something with it. Now I can see it. Now I can measure it. Now I can relate it. Now I can, as a human being with that level of precision that we're limited to, I can actually measure things and make hypotheses and test hypotheses. It becomes something that's actually practical for us to look at and work with. So that's the whole concept here behind using the mole concept. So when 1 mole and 2 moles react to produce 1 mole and 2 moles, one of the most common errors, and what it does not true, this is in red, it says, it is not true that. So this is an untrue statement. I want to make sure that's clear. I don't want you to remember this on the board and say, well, everything up there is true. No, I'm saying this is wrong. It's wrong to say that 1 gram and 2 grams react to produce 1 gram and 2 grams. Why would that be an erroneous statement? Why can't we just measure out a mass and add, because of this equation here, use masses? Different densities, more specifically, different molar masses, right? So we said before that 1 and 2 produce 1 and 2, but because they have different masses, both as it's going to have the same number of masses on the different elements, but in the compound forms, we don't know how that's going to be distributed and what it's going to look like. We cannot say that a particular, by looking at the coefficients, we can't say 1 gram, 2 grams react to produce 1 gram and 2 grams. We can't say that. In some very unique cases, that may be true, but it's hard for me to imagine that because it would have to be, basically, your products would have to be the same as your reactants, so there'd be no reaction. There's got to be some changes taking place, some mixing of the atoms and the molecules to form something different. Otherwise, you really don't have a reaction. And this is one of the most common mistakes because we are going to work it out using the molar bridge. We are going to write down and say, okay, when this number of moles of this and this number of moles of this react to produce this number of moles of this and this number of moles of this, how many grams is that? And so we're going to go through and compute, okay, 1 mole of CH4 is how many grams? And we could, if we knew the molar mass, multiply the coefficient by the molar mass here and end up with a number of grams. And a particular number of grams of CH4 reacts with a certain number of grams of O2, not because it's 2, but it's 2 times the molar mass of O2. Reacts to produce 1 times the molar mass of carbon dioxide plus 2 times the molar mass of water vapor. So we can write an equation and have it be true that uses grams. However, the number of grams does not come from the coefficients of the balanced reaction. When it comes to chemistry, the master unit in reactions is the mole. The moles trump, not Donald, okay? It means they win. Also, not referring to Donald, okay? The mole is the significant thing, which is why on the bridge, the mole is in the center. The mole relates us to mass, and the mole relates us to count, and the mole relates us to molarity, and the mole relates us to volume, but we've got to go back to the mole. And in our chemical equations, the coefficients in front of the atoms and molecules represent the number of moles. We can convert it to grams, but we've got to use the bridge to do it. And we could rewrite this equation in terms of grams, but we have to do the bridge to do it. We can't just use the coefficients. Okay. Is that a strong enough warning to you? Because people will do this. You will do this. You need to be careful. I've got to be talking about moles when I'm looking at an equation. And if I have something other than moles, it's an intentional conversion from moles to that thing. Because I may ask you, with this balanced equation, how many grams of O2 would I need? Knowing the molar mass of oxygen molecule multiplied by 2, you can tell me how many grams that would be. All right. Leave some white space here. Let's go ahead and look at example 7-8, third edition, 266. Is that correct?
264.
What is the mass of nitrogen tri? No, we are actually, should be on example 7. Oh yeah, 7-8. Thank you. And the A and B. Let's go on to 7-8, example 7-8 on 266. Let's do that one. It says the decomposition of hydrogen peroxide into water and oxygen is described by the following equation. 2H2O2, so 2H2O2 liquid. We're going to review this again in a couple days. Decomposes into means it reacts and breaks down into 2H2O in liquid and O2 in gas. If a chemist begins with 2.4 mole, how many moles of O2 will be produced? Okay? I have moles of H2O2, and I'm asking for moles of O2. We need some kind of a relationship in here that's going to move us from moles of H2O2 to moles of O2. And we're going to get that statement of equality from our equation. Okay? Given something and doing a math operation to end with something, we've already talked about that when we use unit multipliers, there's got to be some kind of mathematical relationship that's true. Usually up to this point we've used statements of equality. For example, 1 kilogram equals 1,000 grams. And we know that if we're converting from grams to kilograms or kilograms to grams, we can use that relationship and form a unit multiplier by either putting kilograms in the numerator and grams in the denominator or switching it around. One of those will work to make the conversion for us, depending upon what we're given and what we're going to. In this case, we're given this reaction, and we're going to assume right now that this is a balanced reaction. We could check it real quick. 2 sets of 2, that's 4. 2 sets of 2, that's 4. Okay, 2 sets of 2, that's 4. Oxygens as well. 2 sets of 1 is 2, and 1 set of 2 is 2, and 2 and 2 is 4. Yes, it's a balanced equation. Now we're given that we have 2.4 moles of H2O2, and it's going to decompose into a certain number of moles of H2O and a certain number of moles of O2. How many moles of H2O and how many moles of O2 if we start with 2.4 moles of H2O2? Now, here's what I hope you can see. If this is a balanced equation, and I start with 2 moles of H2O2, how many moles of O2 am I going to produce? If I start with 2, how many am I going to produce? I'm going to produce 2 moles of H2O and 1 mole of O2. Okay? We see that from the equation. If I start with 2 moles of hydrogen peroxide, because the coefficient here is 2, if I start with 2, I will produce 2 moles of H2O and implied 1 mole of O2. Do we see that? Okay. From the equation, okay, 2 produces 2 and 1. Since it's balanced, we know it's potentially true. Because in the lab we produce those products, we know it's true. Okay. So I could say, if I had 2 moles, I would produce 1 mole. Is that a true statement? 2 moles of H2O2 produces 1 mole of O2? I mean, it produces more, but is it true that it produces 1 mole of O2? Yes, it is true. So I use that as a statement of equality to move from moles of H2O2 into moles of O2. Looks like this. If given 2.4 moles of H2O2 times some conversion produces certain number of moles of O2. See my setup? You agree with my setup? Given this, times some math operation to produce some number moles of O2. That's the question rewritten in mathematical form. My statement here, my conversion factor, I have to have, let's say, moles of what? What goes in my denominator? Good, moles of H2O2. Why? Because I want to get rid of moles of H2O2 and end up with just moles of O2. So here you can see moles of H2O2 cancels moles of H2O2. Now, a true statement. I got to relate moles of H2O2. What do I need in the numerator? Does everybody see that I need moles of O2 in the numerator? I need moles of O2 because I need to end with moles of O2. So my setup, moles of H2O2 times something that relates moles of O2 to moles of H2O2. And my units for my answer are going to be moles of O2. With this setup, those are the units that I would expect. Because moles of H2O2 would cancel moles of H2O2, leave me with moles of O2, which is what I am asked for. So my setup is correct. Now the question is, what are the numbers that go in here? I need something that relates moles of O2 and moles of H2O2, and I get that from my balanced equation. So, moles of O2, how many do I have? 1. I have 1 mole of O2, and when I have 1 mole of O2, it comes from how many moles of H2O2? 2 moles. I do the math. So 2.4 times a half is going to be 1.2. I get my statement of equality for my conversion from my balanced chemical reaction formula. For every 2, I get 2 of H2O2, and for every 2, I also get 1 of O2. So we could just as easily take this question and say, okay, given 2.4 moles of hydrogen peroxide, of H2O2, times something to produce so many moles of, what's my other product? H2O. Now this is pretty straightforward, right? Because I've got moles of H2O2, I need moles of H2O2 and moles of H2O. What's my conversion factor going to be? Well, for every 2 moles of H2O2, I produce 2 moles of H2O, and so my answer is going to be 2.4. If 2 produces 2, then 2.4 produces 2.4. Then 10 produces 10. 100 produces 100. You see? Because they're the same coefficient, it's going to be the same in my balanced answer as well. Another way to look at it is, hey, for every 2, I produce 2, and I produce 1. So what's my... this would be 1 to 1, and this would be 2 to 1. No matter how many moles of H2O2 I have, in the end, I'm going to produce half that number of O2 molecules. half of that number. So again, if I have 100, I'm going to produce 50. If I have 500, I'm going to produce 250. And with terms of water, it's going to be the same. So if I have 100 moles, I produce 100 moles. If I have 100 molecules, I produce 100 molecules. It's not true if I have 100 grams, I produce 100 grams. No, that is not true. It's only with regard to counting units. Individuals, dozens, hundreds, scores, or moles. And we're going to use moles because that's big enough for us to comprehend and use. All right? Another problem. Second half of 7-8 says, if a chemist, let me clear this first, and we'll go through this. If a chemist has let's do the composition. Let's write the composition reaction down first. C2H6O. C2H6O. We got CHO again. Decomposes to produce C plus H2 plus O2. If there is 0.234, moles of C2H6O, how many moles of carbon will she get? All right? There's the entire question. Yes, ma'am. They do. So our first step is to ask, is this a balanced equation? Do you see, of course, that it's not? Why? Real quickly, we look at it and say, okay, there's carbon, hydrogen, and oxygen decomposes. Now, writing a balanced decomposition reaction is really easy because everything breaks down into its elemental forms, or elemental molecular forms. So, looking at it, 2 carbons produces how many? C2, so we need 2, right? We have 2 carbons on the reactant side, we need 2 carbons on the product side. And looking at the hydrogen, how many do we have? 6 in the reactant side. On the product side, we have molecular hydrogen. We need 3 of those to get 6. And oxygen, how many do we have? 1. So how do we get 1 oxygen from here? It's 1/2, right? 1/2 of 2 is 1. But we can't leave it in that format, can we? So what are we going to do to every coefficient? Good. Multiply by 2 to get rid of the fractional coefficient. So since we have, this is a whole number 1, whole number 2, whole number 3, fractional 1/2, let's multiply everything by 2, which is going to make this 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, and 2 times 1/2 is 1. Now we have a balanced equation. Yes, sir. What did I use? What? Because my oxygen, I only had 1/2, and I can't leave a fractional coefficient. So to get rid of the fraction, if I multiply 1/2 by 2, I get 1. So since everything was a whole number, multiplying everything by 2 makes it true. Okay? So I multiplied everything by 2. Now we have a balanced equation. Let's check it real quick, just to make sure. 2 sets of 2 is 4. There's 4. 2 sets of 6 is 12. 6 times 2 is 12. 2 times 1 is 2. 1 set of 2 is 2. We have a balanced reaction equation. Now we're given that we have 0.234 moles of C2H6O, and we're asked how many moles of carbon are produced. Well, if I had 2, I would produce 4. You see that? If I had 2, I would produce 4. What's my multiplier there? How do we go from 2 to 4? It's twice as much, right? So here's the shortcut. If I have this, how much am I going to have? If I've got 0.234, I don't have 2, I have got 0.234, how much am I going to have of carbon? Twice as much. See? to go from 2 to 4 is to multiply by 2. If I take 2 times 2 produces 4. So if I 0.234 times 2, and it produces 0.468 moles. You see that? I start with 2 and I produce 4. So if I start with 0.234, I produce 0.468. Because I'm multiplying 2 by 2 to get 4. So this times 2 to produce this. The relationships are the same. The proportions are the same. The long way of doing that is to say, okay, I'm given 0.234 moles of C2H6O. And I need some relationship that converts it to produce a certain number of moles of carbon. Looking back at my balanced reaction formula, I need something that relates moles of C2H6O, because this is my numerator. I need to lose it in my units, and I need to convert it to moles of carbon so I have it in my numerator, so I have it in my answer. I need some relationship from this equation that relates moles of C2H6O to moles of carbon. Well, the relationship is for every 2 moles, comes from right here, for every 2 moles of C2H6O, it produces 4 moles of carbon. So whatever my number of moles is, times a multiplier of 4 over 2, which reduces down to what? This whole thing reduces down to 2, right? See, it doubles it. So whatever I have in terms of moles of C2H6O, I can double it and know that that's the number of moles I'm going to receive, that I'm going to end up with in carbon. I'm going to double it. If I said I have 0.234 moles of C2H6O, how many moles of hydrogen gas am I going to produce? Pardon? Multiply this by 3. I go from this, I multiply by 3 to get that, right? So I'd multiply this by 3, and I would end up with how many moles of hydrogen would be produced. And also, given this, how many moles of oxygen are produced? Well, to go from 2 to 1, I multiply it by 1/2. And so if I have this many, 0.234, I would multiply that by 1/2 to determine how many moles of oxygen are produced. Okay? So your relationships in your proportions are all going to come from this balanced reaction equation. Looking at the coefficients and saying, okay, when I have this reactant, it produces these products, and it produces them in these proportions. For every 2, I make 4. For every 2, I make 6. For every 2, I make 1. Let me go through and apply that proportion to whatever I start with, and that'll tell me how much of each of these things I end up with. Let's go ahead and work on your own 7-Eleven. It's more than just a gas station or a junk food store, right? 7-Eleven. For those of you in second, I'll write it on the board. Make sure we're doing the same one. It says, a chemist obtains 100 moles, 100.0 moles of ammonia, NH3. Of ammonia, NH3. If he allows this sample to decompose, how many moles of hydrogen gas will be produced? Now, decomposition reaction means we've got NH3 decomposing, right? NH3 is reacting in decomposition. What is it going to become? It's going to become N2, because it's a homonuclear diatomic, right? And H2. So what's the first thing you're going to have to do? Balance the equation. Then make a relationship between the number of reactants times the relationship to produce the amount of product. We'll go ahead and do the moles of hydrogen, but we'll do this one first, but then we'll also do this one second, nitrogen. Okay? Go ahead and take a few minutes and get ahead of me so that I can confirm that you understand it. Because if you write something down, you actually try it, then as we go over it, if your work looks like our work, then you'll say, hey, I do understand this. And if it doesn't, even if you think you understand it, you'll go, wait a minute, oh, I thought I understood it. I don't. I need more help. I need more work. So take a few minutes now to do a good effort on getting this thing rolling and answering it, and then we'll start working it together. What we're doing right now is a very significant portion of what's known as stoichiometry. I think the next module is all about stoichiometry. One moment. Let me see real quickly. I believe the next whole module is called stoichiometry. So this is the fundamental part of stoichiometry that you need to understand. And there's going to make the statement in the next module that stoichiometry is chemistry. If you don't understand stoichiometry, you really don't get chemistry. So this is beyond the fundamental makeup of an individual atom. What we're about to do is the most significant portion of the course. Yes, ma'am. We're starting with how many moles of hydrogen, but we're also going to answer the question, how many moles of nitrogen? But we're going to start with hydrogen. Now we can balance this using the shortcut method, or we can balance it using the matrix method. Matter of fact, we have about 4 minutes left. No, you can skip the phase for now. Just worry about the fundamental molecular forms. Don't worry about the phase. What we're gonna try to end up with what is going to be the number in front of here first of all, and then given 100 moles of this, how many moles of that will we produce? Okay. Now for time, I'm going to go ahead and press on with this, because as we look at this equation, I've got 1 nitrogen over here, I've got 2 in my product side. What do I need to do at first, at least, to balance my nitrogens? Good. Put a coefficient of 2 in front of my NH3. That'll give me the 2 nitrogens I need to form 1 nitrogen molecule, but I also then have 6 hydrogens. So how do I use up the 6 hydrogens over here? Coefficient of 3, right. So that's my balanced equation, using the shortcut. If you need to use a matrix, do it. Whatever method works for you to balance the equation. That'll take more time, but if that's the method you have now, good. If not, if you're ready to move up to that, hopefully start seeing that and start doing it real quickly. Now we have a balanced equation. Now the question is, if I have 100 moles of NH3, how many moles of hydrogen do I produce? So, here we go. If I've got 100 moles of NH3 times something that's going to relate moles of NH3 to moles of H2 equals moles of H2. That's my basic setup. My relationship between NH3 and H2, I have 2 moles of NH3 produces 3 moles of H2. So my multiplication factor is 1.5 times. 3 divided by 2 is 1.5. So 1.5 times 100 is 150. It produces 150 moles of H2. Okay? Now let's look at the other relationship. If we have 100 moles of NH3, and I need something that's going to produce the number of moles of N2. Well, my relationship here, when I have 2 moles of NH3, it produces 1 mole of N2, so it's a half, and the production here is 50 moles of N2. Okay? It produces 50 moles. Shortcut way, 2 to 3 is 1.5. 2 to 1 is 1/2. I will see you tomorrow.